So it's time to start the afternoon session. And the first speaker now is Alejandra Castro from Cambridge, and she will tell us about engineering gravitational theories in AdS CFT. Please.
Okay, thank you. Thank you so much for the invitation. I might start doing this throughout the talk.
But I'll tell you.
Please, yes. Remind me to keep my mic near to my mouth. I'm not used to talking in this way. But in any case, thank you for the organizers for asking me to give a vision of what I think is interesting, is exciting, and, well, of course, related to the stuff that I do. So that's what I'm going to attempt today. I warn you already, I will prompt it throughout the presentation. I think I prepared too much, but it's okay. So if I don't get to cover everything, the slides will be available online, yes? And so then you can look at what the topics maybe that I didn't cover. But okay. So let's get started. So what is the idea that I have in mind? So at the center of what I'm going to be telling you today is the gravitational path integral, okay? So as we all know, this is basically an object that I've written here formally as something where you're integrating over all possible geometries and topologies. So over the gravitational degrees of freedoms, you will have fields involved, and they will be weighted by their action, and there's going to be basically some boundary condition that you're going to put on this object. Now, in recent years, this has been revisiting this object, quantifying it, computing it, has been incredibly productive. So in particular, two things that it has been quite useful at are basically underlying, for instance, the microstate description of black holes, computing black hole entropy, reproducing the page curve, quite surprisingly. So although this object has been introduced by many decades by now, it's only recently that we know that there's actually a lot to learn about gravitational path integrals, more than we expected. Now, one of the lessons, and here's where I will start also making connections with other visions that we heard yesterday, is that there's cases actually, very simple models, where we can compute this path integral exactly, okay? And one of the cases, so this is, for instance, 2D gravity, 2D JT gravity is one of the most famous cases nowadays, is that when you have access of doing an exact computation, the way that you have to think about the answer that you get is in terms of a coarse grading, okay? So you don't get a density of states that is compatible with a discrete spectrum. You get something that looks basically like that curve. You get like a spectral density. And so in connection to what Jan was basically guiding yesterday, there's this coarse-grained picture of how do you think about quantum gravity. But I am of a more discrete mindset. And so what I want to do is take a different perspective. So I want to say, let's imagine for a moment that I know what quantum gravity is. Okay, that we have a candidate. I'm a string theorist, so I'm confident to say that I can pretend that this is something I know. Okay, so in that case, you will have some discrete spectrum, as I'm trying to kind of cartoon here. So there will be some discrete set of eigenstates. It will look chaotic, that's fine. But there was going to be something that I should be able to compute, in particular, like something like trace of e to the minus beta h. Okay, now, even if I believe that there's a theory in quantum gravity, there's a UV framework for which this is true. One of the open questions is basically, can we derive this in detail? From here, can we derive the gravitational path integral in detail? Okay? So can I make a very specific and precise connection between these two concepts? This is what I want, okay? This is what I think it's an important question to ask in a theory of, in a UV complete theory of quantum gravity. Now, you would say, for instance, in the context of AdS CFT, is that the answer we're expecting, we have the belief that, yes, there should be a situation where this is possible, because when we have backgrounds that arise from string theory, there's a single Hamiltonian in these dualities, and you should, in principle, see that trace of e to the minus beta h is equal to a gravitational path integral, right? But we don't know actually how this emerges, okay? So there's not a simple example where you explicitly compute a trace and you see it exactly as a gravitational path integral, okay? We have a lot of indications and hopes, but it is not something that you would say, yes, we have derived the gravitational path integral from this discrete spectrum. But I already see an objection to that statement. Or what's that?
Are questions allowed at this point? Okay.
What's that?
No, it's okay. So, but isn't it the gravity supposed to be a low effective description? And I mean, you shouldn't expect exact equality.
Quantum gravity as something that has a UV description.
Yes, but you don't expect that doing the path integral over low energy degrees of freedom will give you the exact answer.
You will have to add, like that's the point.
Yeah.
Like how do you see basically, in some sense, if you're telling me that there's a duality, there's an equality between two things, both sides have to be well defined, right? And so from the perspective of AdS CFT, one side of that equation you're quite comfortable with, right? You do not object to computing the trace over the Hilbert space in a CFT. What is the gravitational computation that you're supposed to do on the AdS?
No, I mean, philosophically, I agree, but just the formula seems to me too naive, but okay. Yeah.
The other side of the equation is what I mean by quantum gravity. That will mean for me that I understood what quantum gravity is. If I can't make sense of that other side of that equation, I would not admit to knowing what quantum gravity is. So that's part of like the vision. We want to know what quantum gravity is. Okay. But we're not there yet. I think this is not something that we would feel like comfortable at establishing, that we understand how this, if you want, starting from that trace, basically, how do you get to this low energy description systematically, case by case? This is something that is, we don't understand. We have indirect evidence. There's pieces where we think that this is true, but it's not like a direct computation. And so this gets at the questions of basically, what are the rules controlling the gravitational path integral in these cases? Because cases where we can compute the gravitational path integral, we don't get this answer. So there should be some differences. There should be some modifications. And something else that is important that I will highlight as we go along is that if I only have gravitational degrees of freedom, metric degrees of freedom, I don't think we're going to get to this discrete, basically, description. And so there has to be an interesting interplay about how gravity talks to matter and how maybe there's modifications there in order for me to get this discrete spectrum. So what I want to do during this presentation is basically give you three sharper questions, because how I presented it to you and how it's already illustrated by the reaction is maybe set up in a way that is too broad. So I want to narrow it to three more specific questions of what I think are useful ways in understanding this equation. So the first question is basically in the context of AdS CFT, so I'm always going to be talking about it in the context of AdS CFT, is basically trying to understand what are CFTs that can capture classical properties of gravity. Okay, so we have many examples, but they're examples. I don't want examples. I want mechanisms. I want rules. I want classifications. Second, are there consistency conditions for the CFT that have an imprint in the gravitational path integral? So are there things that we can detect, that we can learn from the CFT, and they will tell us, this gravitational path integral has to reproduce these answers, and it gives us basically an understanding of what are possible effective field theories. And I'll show you an example of this. And then the last question is basically, given a CFT, how do you organize it such that quantum gravity is manifest? Okay, so how do we rearrange things in a way that it pushes us forward? And so yesterday I was going through these three questions, and I ordered them in this way here in this slide, but then when I was organizing the rest of my slides, it's like, which one should I explain first? I'm not going to have enough time to go through all of them. And so I made an executive decision, and we're going to start with the last one, okay? So we're going to first ask, given a conformal field theory, how can you organize it such that quantum gravity is manifest, okay? So that you can start seeing the hints of this gravitational path integral that, as you go along. And so, okay, so let's start with number 3. So let's just pick as an example, this is old work that I've done, but I want to illustrate the point. Let's just grab 2 CFTs that are well known, they're solvable, they're loved by condensed matter physicists. So let's pick the Ising model and the tricritical Ising model, okay? So the Ising model at the critical point is a CFT with central charge equal to 1/2. The tricritical Ising model is at the critical point, it will have central charge 7/10, okay? These are CFTs that are solved. There's everything that you want to know about them, they're known. And in particular, something that you know about them, that you can open the Francesco, go to the appropriate chapter, the partition function is exactly known. And how I'm writing it here for each of these theories, I'm favoring basically how do you organize the spectrum in terms of Virasoro representations. So there I'm basically have a sum over the allowed primaries, and there's a character associated to each primary, okay? Known system, solved, done. Is this gravitational? How do I see gravity from these examples? And so you might ask the question in the way that I was asking that before, is there a way how I can rearrange this partition function such that it looks like a path integral over metrics? And so before I tell you what the answer to that question, we should think about what does it mean for it to look gravitational, right? So it's a question like, how do you see gravity manifest itself in this type of situations? And in this case, because I have a 2-dimensional CFT, the question is in AdS3 gravity. And in AdS3 gravity, at least from a saddle point of view, I know what are Euclidean solutions that will contribute. So you start with a cylinder, Lorentzian AdS, you make time periodic, so that introduces a beta, and we know that there's various saddles that contribute, such as thermal AdS and the BT set, and they're related by basically a modular transformation. Here I just illustrated one, the S transform, but in general you have a whole family of modular images of these saddle points. And so the expectation from a gravitational point of view, if you only have metric degrees of freedom, is that this path integral, as you compute it, should be organized as a sum over images of the vacuum contribution, where the vacuum contribution is basically the contribution that comes from thermal AdS, and that the images will give you basically the black holes. So this is what we expect roughly from a gravitational path integral. So okay, that's the lamppost. Does the Ising model and the tricritical Ising model allow a rewriting in this way? And the answer is yes. Okay? It's not how you would write it. You're not going to find this in the Francesco. They're going to write it as the first line. But you can actually write it for these 2 cases. You can actually rewrite that partition function as a sum over images. Okay? So this is just as a thought example, as a toy model of like, what do I mean by asking you rewrite things in a way where gravity might become more manifest, okay? So in the first equation, I'm favoring Virasoro symmetry. In the second equation, I'm favoring basically the saddle point of view, okay? That's basically the contrast between the 2 of them. You're not losing information, but it's just basically giving you a different perspective on how you interpret the model. Now, of course, this toy model is really toyish. It's not great. There's a question.
How can you expect to have for C, which is not large n, duality with gravity?
It's remarkable,
and
right?
Not with the full string theory. And also, where is the strong coupling in this game?
Well, this is related to my remarks and why this might just be viewed as an academic exercise. Because, for any minimal model, you can always write a version of this, but it will not be the vacuum character that you're summing over images. It will be something else. But basically, just to be clear, these 2 minimal models are the ones that admit this very specific characterization. In the next slide, I'll tell you how it generalizes to other rational CFTs. And coming to your question, the reason why this is not like a great maybe lesson for AdS CFT is that the value of the central charge is fixed, right? And it's really low. And so I don't have anything else to say about that. Like, it's not like, that's why there's no large n here. N is 1/2. So I think it will be interesting to see, like, well, I don't know, is the Ising model part of the string landscape? I guess yes.
You work with string theory, but not to gravity.
Right, it will be a string theory, fine. But it's kind of interesting that you already see some hints of what that string theory, that theory of quantum gravity, why would it be amenable to it? And so why could you maybe formulate a duality for this system in this case? But in any case, this is basically like a big drawback of what I'm showing to you here. But more has happened, so these are all results. They're more than 10 years old. But recently what happens now and nowadays is that the way that I think that you should be thinking forward is like try to rethink how you organize your quantities in a CFT. So because we read Di Francesco, we like to think of it in terms of like this number of primaries and these characters. But there's been recent developments. I'm putting here some references for you so you can look at those papers where they say, okay, don't write your CFT partition function necessarily in that way, okay? So one way how you maybe want to write it is have a decomposition for something that will have an arbitrary value of central charge, something C bigger than 1, where you have a part that is a sum over images, and it's images over the light part of the spectrum with an appropriate definition of what it means to be light. And then there's a spectral part of the answer. And the spectral part, for instance, related to what Jan was talking about yesterday, this is the part that is going to contain your chaos, okay? This is the part that is going to be perhaps compatible with like this random matrix type behavior. But this is basically a push to say, reorganize your way of thinking, reorganize your structures, try to think about CFTs in a different way, okay, such that maybe these coarse or chaotic features come about. Now, it has two motivations besides AdS CFT. Well, there's one motivation that it comes like if you start organizing CFT partition functions in this way, it will give you a nice interplay about like how quantum gravity plays with quantum matter, what are the rules in this GPI and how do you quantify it. But also, it should be said that we're terrible at classifying CFTs, that have central charge bigger than 1. And so that first equality is not actually very useful. We've not been able to bootstrap CFTs that are irrational, in a sense, by taking this Virasoro perspective. And so a way, if you don't care that much about quantum gravity, but because you care about the space of conformal field theories, this might be a useful way also how you might want to solve for the conformal bootstrap and how you might want to think further about what does it mean to describe one of these like very strongly coupled, very chaotic and messy CFTs. And what gravity in some sense is maybe telling you, 10 minutes, okay, is that you really need to rethink how you organize the structures. Okay, but maybe you're like, no, I don't want to think about CFTs in terms of new observables. I want to organize them as I go. Fine. So let's go to the first question that I had, and let's take maybe a more traditional point of view of how would you go about in understanding what does it mean for a CFT to be holographic. So now, when I talk about holographic CFTs for the rest of this part, I really mean a CFT. Holographic here will mean that it's a CFT whose gravity dual has a low energy effective field theory description. So to satisfy Scobie's question, like I'm now interested in these large N CFTs. I'll move away from the Ising model. And so what we know from AdS CFT is that there are a few properties associated to these CFTs. So we know we need large values of the central charge if you want this low energy description. You want a sparse spectrum. Basically, in the language of the CFT, you don't want a lot of light operators. You want this generalized free field behavior, so you want a factorization of correlation functions. And there's more properties that you might associate. But something that I think should be very much recognized in the community is that there's a reason why I didn't write a full list. Because these are things that we know happen in examples. We know that they're important, but I don't know if these are basically sufficient conditions or if they're merely necessary. And how stringent are the conditions? Maybe if I impose a couple of them, I will already get the other ones for free or not. Okay? So the interplay between these conditions are not fully understood. And basically, the question that I want to address here is, can we engineer CFTs that satisfy this criteria? So if I ask you, build for me a CFT that complies with this, that are not the ones that we know already from string theory, can you do it? And so to illustrate that this is not like an impossible question, this is where my engineering hat comes on. It's like, okay, so let's build those CFTs. So what do? You have to pick a material. What we picked, we said, let's look at symmetric product orbifolds. So these are basically, I'm not going to give you a whole lecture on this, but there in that corner, I wrote a very short definition of what I mean by symmetric product orbifold. Tensoring, adhering, and modding it out by the symmetric group. Now, these are theories that we picked because they have a lot of mathematical and analytic control. They're familiar. One of the examples shows up in the D1, D5 CFTs. They have very compelling features for AdS CFTs, and their large M behavior seems to be quite robust. Okay? And so then you can ask the question, which of these symmetric product orbifolds could admit in their moduli space basically a point where you would have a dual supergravity description. Okay? And so the strategy is basically, let's start imposing conditions to see if I should call any of these examples something that is connected to a holographic CFT. So the picture that we have in mind is basically the following. So symmetric product orbifolds, for various reasons, they appear as like the weakly coupled description in your moduli space. So there will be like, if you want, the tensionless limit of the string theory. But then there should be a marginal deformation that in principle should have a strongly coupled point, and that's where you're going to see your theory of gravity. So the question is, if you grab any symmetric product orbifold, can you basically establish the existence of that strongly coupled point? And the answer, so we basically then here draw our universe of all possible symmetric product orbifolds. For simplicity, let's just talk about supersymmetric cases, because there I actually know what I mean by a moduli space. And you can ask, okay, so how many of them do you think have this strongly coupled point in their moduli space? The answer, most of them won't, okay? So most symmetric product orbifolds don't have a strongly coupled point, and that we could detect from the elliptic genera. So by computing the elliptic genera in these cases, we saw it's a protected quantity. It will not be compatible with having a holographic CFT. But there are two, what we did spotted some non-trivial features here. So it's not all gone, because we know that, for instance, D1, D5 is there. So there should be at least some positive cases. And there's actually two like little spots in this space, in this swampland of green. And so the first spot, the red one, is basically symmetric product orbifolds where you do have basically a protected deformation. 5 minutes, yeah. I will not go through the third topic. And you also have a sparse spectrum in the elliptic genera. Now, a condition to be in that red region is that the central charge of what you put here in one of the copies has to be less than 6. And lucky you, D1, D5 sits exactly at C equals 6. So string theory was at the edge of that classification. But then we quantified for lower values between 1 and 6, we quantified what are other CFTs that meet the same criteria as the D1, D5 CFT, and there's many of them. In particular, there's a whole class of any n equal 2 Virasoro minimal model will satisfy these two cases, and then we also have a whole list of examples between 3 and 6. Okay? But now, because I'm running short on time, let's go through the second corner here. And the second corner is also interesting because this is a case where you also have a moduli space. You will have a marginal deformation that is basically of the same nature as I was describing before, but these symmetric product orbifolds do have a Hagendorn behavior. So these will be examples that will never have a holographic point. But what this teaches you is that, for instance, having this moduli space is not enough to guarantee a holographic CFT. So you need more than demanding that you have a suitable coupling that you can turn on. But also, it also seems like every time that we were complying with a sparseness condition, the moduli space came for free, in a sense. So this illustrates like what is the stringiness, like how stringent is one condition versus another. And so then the task here, so I think this exercise illustrates the point, and I ran out of time probably, is that we can basically, if we pick our materials appropriately, we can really try to understand what are differences between different CFTs. And this whole discussion has just been from the CFT point of view. And so if you want, a challenge is, tell me if I imposed enough conditions. Did I have sufficient conditions? I imposed conditions that are necessary, but it's not clear that they're sufficient. So can you build the gravity dual of these, or the string dual? Go for it. And if you can't, it's great, because then we will learn that there's a more stringent condition, that there's actually, I have to impose something else, and that will lead to something that will have a connection to gravity. And so this is part of understanding the mechanism of why these examples work or not. Okay, so I'm at -2 seconds, -3 seconds, and -4. Okay, great. So I'll, this one was about actually, this is the last question that I had, is that if there are consistency conditions in the CFT that have an imprint in the GPI, and this actually brings me back to black holes, and again, supersymmetric black holes, where we're much better at computing the path integral, and it actually relates to an index in the CFT, and we're also quite good at computing indices in the CFT. And in this case, actually, what's interesting to look at is the quantum corrections of the black hole. So maybe let me just go to since I don't have enough time, to this version of the side. So we're mostly used to like looking at just the area of the black hole, but from the gravitational path integral, you can also get the logarithmic correction to the area. And there's a counterpart derivation of that from the point of view of the microscopic description, and in cases, explicit instances of the correspondence, people have worked really hard on doing both sides of this computation, and there is an agreement, okay? There's a very nice agreement between these two sides. But there's also something interesting that happens here, and let's take a case of AdS4 black holes. So what I want to illustrate here is that, for instance, if your EFT is 11-dimensional supergravity, and you compute this logarithmic correction, so Marcos can tell you all about how you compute that logarithmic correction. It's something that is just a rational number, like it's integer, half integer, and it's a quite simple thing, like, well, you still have to be careful, you can get the integer wrong, but it's just a number. Now, if you do it from a perspective of AdS4, and you just have a finite number of fields in this EFT, this logarithmic correction is going to depend on the parameters of the black hole in a non-trivial way. It's not going to be a rational number. And the thing that is curious that I like to highlight is that at least every time someone has computed this logarithmic correction from an index, I have never seen an example where that coefficient depends on ratios of charges. And so you can guess here what this can teach us. This can teach us something, for instance, about scale separations in AdS CFT. This can tell us you cannot UV complete a theory of quantum gravity in AdS4 if you just have finitely numbered fields. Of course, this side here, what we really need to have, it's a better understanding what I'm highlighting in green there in the bottom. We really need to understand what is the meaning of that logarithmic correction in the CFT and establish if it's always something that is independent of the parameters, or maybe there are CFTs that I'm just not familiar with, where this thing maybe can depend on the ratios. And it's just a coincidence of where I'm looking in AdS CFT that they happen to be very simple things. So with that, I'll conclude. Done? So these were the 3 questions that I presented very quickly. And I put here underneath each of them basically either 2 aspects or 2 further sub-questions that I think will be interesting to pursue. And I hope members of this collaboration might find this fun to work on. So, done. So think out of the page, like in an AdS CFT, you're at the boundary, Go explore the book, come back.
We have a question.
Not funny enough.
Yeah, so you were looking at constraints on the CFT that might lead to a theory of quantum gravity. But in the last few years, there have been several proposals for actually quantum gravity, at least have a low energy effective description of quantum gravity corresponding to an ensemble average over CFTs.
Yeah.
So,
Yes.
is there a particular reason for expecting,
No, so that's
single
why.
CFT being a very good description of quantum gravity in arbitrary dimensions?
Well, okay, it depends. Okay, so this is why I started with what happens if you just compute a gravitational path integral. So if you just compute a gravitational path integral in solvable models of gravity, then you don't get this discrete properties. You get the spectral density, which is the ensemble description that you're. So when I wrote down that curve, that's what it meant. That if you get like a spectral density, you're getting on a, usually it's interpreted as some type of coarse graining or ensemble. And the example is an ensemble over theories. In general, just to be honest, like it's not always clear what you're coarse graining over. So that's also a big important open question in the field, like what is it, what are you coarse graining over? But okay, in the case of JT gravity, it's Hamiltonians. But in some sense, I don't think that's the end of the story. Because what I learned from string theory is that there should be cases where the spectrum is discrete. And so I just decided, because it's my vision, that I want to focus on those cases where I'm expecting from the UV a discrete spectrum. And then what does that tell me about the effective gravitational description? So what do I need to modify from this low energy point of view such that I get that picture? So how do I resolve the factorization problem? How do I resolve like all these features that seem to not be compatible with it? Because I do think that there is a landscape of gravitational theories, and this is where it connects also with what Irene was saying, that there should be a landscape of effective field theories of gravity that do admit a UV completion, and this is basically very aligned with what she was saying yesterday. What are these theories of quantum gravity that have a UV completion? And by UV completion, I mean, I want my thing to be discrete. It can be chaotic, it will be strongly coupled, but please, let's keep it discrete. And yeah. But yeah. In any case, we can chat later about like the other perspective if you want to push this ensemble average interpretation.
More questions?
Very nice talk. So you promised that you make a comment why higher minimal models don't have gravity duals. And then maybe I missed this point.
Yeah, it's because, let me go back to that slide. They will have a gravitational interpretation, but not in terms of pure gravity. So it will be something that will have more stuff in it. So any minimal model, so let me point to this equation because it's a bit more general here. So for any rational CFT, you will always be able to write the partition function in this way. This spectral part is going to be trivial. It's going to be exactly 0. But what your image is, the C light, is not the vacuum character, and that's what I meant by pure gravity. So the seed that you put in there is a combination of basically every state that it's polar, basically. It's between minus C over 24 and 0. And so I'm putting the vacuum at minus C over 24. And so any primary that is between minus C over 24 and 0 is what I'm calling light. And that from if you can still interpret it gravitationally, but it will be a theory that will not just be pure gravity, it will be gravity plus matter. And so that's what I meant in the previous slide, that because in the previous slide, I did write vacuum as the seed, and that's very, very specific to these two models. And it's because these two models are the only minimal models that don't have a primary between minus C over 24 and 0. So the C light here is actually the vacuum character, but any other minimal model will have a few states in between.
And is it possible to test this with some other observable, not the partition function, but some correlation function?
Well, then it's a little bit more tricky for the objections that I had, then I'm a little bit more nervous what I mean by quantum gravity. But there has been papers, follow-ups, where they did higher genus Riemann functions. Riemann surfaces. And so there's been some follow-up since there. Actually, from the condensed matter community, there was some interest in reorganizing these things in this way. So there's I can point to you to some papers that came after, but it was like the higher genus partition functions.
Okay, so in your time, I would very quick and a very quick answer.
I'm sorry.
Thank you for your talk. So in this talk, you've posed the question which CFTs may have a gravity dual, if I understood properly. I would like to ask the reverse question. What gravitational theories may have a CFT dual? Is it an equivalent question?
In a sense, it's a bit equivalent, but this is where I think you need a synergy between the two sides. So I think there has to be push on both sides. But right now, I'm hoping, my perspective is that I think the CFT can teach us a bit more on like, when we add matter, maybe what do you expect the matter to interplay with gravity such that you start seeing some of these things get erased or removed. But it will come from a little bit from both sides. But right now, yeah, I was pushing more the CFT. Just because I know that I'm starting with a discrete spectrum from the get-go.
Okay, it's a bit late, so let's postpone further discussions for the coffee break, and let's thank Alejandra again.